Hi, welcome to my video in ML from Scratch series. Today I want to take a deep dive into principal component analysis, or PCA. In this video we'll derive the PCA algorithm using basic linear algebra and calculus and then implement it from scratch in Python. PCA is a popular dimensionality reduction algorithm with applications ranging from data visualization to algorithmic trading, and I'm really excited to share this algorithm with you. Let's get started. Let's start off with a quick overview of PCA and its applications. We'll define the problem mathematically and then derive the PCA algorithm from first principles. We'll conclude with from-scratch implementation of principal component analysis in Python. PCA is a dimensionality reduction algorithm which takes high-dimensional data and projects to a low-dimensional space in a way that maximizes the variance of the projected data. On the right, we see the PCA of the iris dataset in which we project four-dimensional features onto a two-dimensional space. We can visualize three clusters of points that correspond to the three types of iris labeled in the figure. Let's formulate the problem mathematically. Let xi be a d-dimensional data vector and let zi be our l-dimensional projection with l less than d. Our goal is to minimize the reconstruction error. Here xi hat is the reconstructed vector equal to wzi, where zi is our low-dimensional projection. Thus multiplying w by zi lifts zi into the high-dimensional space. W has dimensions d by l and it's an orthonormal projection matrix, which means that transpose of w is equal to its inverse. Let xi be a reconstructed vector. We can multiply both sides by W transpose and write our PCA projection Zi as W transpose xi. Our goal is to find the optimum projection matrix W transpose. We will show soon that the optimal projection matrix W is the one that maximizes the variance of the projected data and is equal to L eigenvectors corresponding to the largest eigenvalues of the empirical covariance matrix sigma, where we assume that xi, our data vectors, are zero mean. To get to the general solution, let's start with the best one-dimensional solution. In other words, let's find W1 vector such that the variance of the PCA projection Zi1 is maximized. Let's compute this variance. By definition, the variance of Z1 is equal to expected value of Z1 squared minus the square of the expected value of Z1. We can write out the first term as an average of Zi1 squared and the second term is 0 by the zero mean assumption of our data vector xi. Recall that we want to maximize the variance of the projected data. Let's plug in the expression for the variance from the previous slide. We can expand Zi1 squared and recognize the average as empirical covariance matrix sigma hat. Finally, W matrix is an orthonormal, which means we have a constraint that inner product of W1 with W1 is equal to 1. We can include this constraint in our optimization problem by writing out a Lagrangian, which simply moves the constraint into the objective function, taking the derivative with respect to W1 and setting it to 0. We are maximizing the expression below, which consists of our original objective, variance of the projected data in 1D, and orthonormal constraint term multiplied by Lagrange multiplier lambda 1. Taking the derivative with respect to W1 and setting it to 0 gives us the following expression. Sigma W1 is equal to lambda 1 W1, in which we recognize that the optimum W1 is an eigenvector of empirical covariance matrix sigma. If we multiply both sides by W1 transpose, we get the projected variance is equal to the eigenvalue lambda 1. Since we're trying to maximize the projected variance, we want to pick the maximum eigenvalue. In other words, the optimum projection W1 is the eigenvector of the covariance matrix that corresponds to the largest eigenvalue. We can repeat this process by subtracting the first principal component W1 from our data vector xi And we'll discover that sigma W2 is equal to lambda 2 W2 and so on. We can use induction to prove that general result that the PCA projection matrix W consists of L eigenvectors corresponding to the largest eigenvalues of the empirical covariance matrix. Now that we have a better idea what PCA algorithm is about, let's take a look at a Python notebook where we'll implement the algorithm from scratch. Feel free to read through the theory once again at your own pace. The notebook is linked in the video description below. I'm going to go straight to the code. We start by importing NumPy and matplotlib and fixing the seed for reproducible results. We define a PCA class. In the constructor we set the number of principal components with default value of 2. Next, we define a function for computing the empirical covariance matrix. Finally, we define a transform function in which, given the input data, we first find the covariance matrix sigma. Then, using NumPy, we find the eigenvalues and eigenvectors of sigma. We then sort the eigenvalues from largest to smallest and pick the top n eigenvectors that correspond to the largest eigenvalues. Finally, we project the input data onto our principal components. Let's try our PCA algorithm on a random matrix with values sampled from a uniform distribution between 0 and 1. Here in the output we see the two principal components and the scatter plot showing PCA projection of the random matrix. And we're done. I hope you have a better understanding now of this popular dimensionality reduction algorithm. Thank you for watching. I hope you enjoyed this video. If you're interested in more educational ML content, please hit like and subscribe to my channel. Looking forward to seeing you soon.